Identifying inconsistent systems, no solution. Welcome, everyone. To begin today's lesson, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on how to find a unique solution for a pair of linear equations, specifically using the substitution method. Usually, this process leads us to a single, specific point where the two lines meet. However, it is important to realize that not every system of equations behaves this way. Not every pair of equations will result in a single, unique point of intersection. As we move forward, you will see that in certain cases, when you follow the algebraic steps we've practiced, the math will lead you to a conclusion that suggests no solution exists at all. When you encounter a situation where the equations simply cannot be satisfied at the same time, we refer to such a system as an inconsistent system. In the next slide, we will dive deeper into exactly what this looks like both algebraically and geometrically. Understanding the concept. At its core, an inconsistent system is simply a pair of linear equations that has no common solution. To put that in simpler terms, there is no pair of values, x and y, that can satisfy both equations at the same time. So, how do you spot this while you are working through your algebra? I like to call this the algebraic signal. When you apply the substitution method to an inconsistent system, you are going to notice a very specific pattern. First, the variables, such as x and y, will completely cancel each other out during the substitution process. Second, you will be left with a mathematical statement that is clearly false. For example, you might perform your calculations and end up with a statement like 0 equals 7 or -4 equals 2. Since these statements are logically impossible, we know that 0 definitely does not equal 7. We can confidently conclude that the system has no solution. But what does this look like if we step away from the algebra and look at a graph? This is our geometric interpretation. If you were to plot the two equations of an inconsistent system on a coordinate plane, you would find that the lines are parallel. Now, remember that parallel lines have the exact same slope, but they have different y-intercepts. Because they are running in the same direction but starting at different heights, they will never intersect, no matter how far you extend them. And since a solution is defined as a point of intersection, the lack of an intersection means there is no solution. Now that we've introduced the term, let's dive deeper into what an inconsistent system actually represents. In our previous lessons, we were used to finding a specific point where the equations met, but here, that point simply does not exist. In the next slide, we are going to look at a real-world scenario involving taxi fares to see exactly how this false statement appears in a practical problem. Real-world example, the taxi fare dilemma. Now that we have covered the theoretical definition and the geometric idea of parallel lines, let's move away from the abstract and look at a real-world example to see how this actually plays out in a practical context. Imagine you are trying to decide between two different taxi companies, Company A and Company B, and they both have slightly different pricing structures. For Company A, they charge you a fixed base fee of $5 plus an additional $2 for every kilometer you travel. Company B, on the other. Key takeaways. First, let's revisit our formal definition. A system of equations is officially called inconsistent whenever it has no solution. This is exactly what we saw in our taxi fare example. There was simply no point where the two costs matched. Now, how do you spot this while you're actually doing the math? Keep an eye on your algebraic result. When you are using the substitution method, you'll know you're dealing with an inconsistent system if the variables completely vanish, leaving you with a mathematical statement that is clearly false. For instance, you might end up with something like A equals B, where A is definitely not equal to B. If you see a contradiction like 0 equals 5, that is your signal to stop and conclude there is no solution. Geometrically, we can visualize this by looking at the graph. The lines represented by these equations are parallel. Because they have the same steepness but start at different points on the y-axis, they will run alongside each other forever and never intersect. Finally, for those of you who like to use a more formal test, there is a specific condition you can check using the coefficients of the equations. If you have two equations written in the form a sub 1x plus b sub 1y plus c sub 1 equals 0 and a sub 2x plus b sub 2y plus c sub 2 equals 0, the system is inconsistent if the ratio of the x coefficients is equal to the ratio of the y coefficients, but that ratio is not equal to the ratio of the constant terms. In other words, a sub 1 over a sub 2 equals b sub 1 over b sub 2, but this is not equal to c sub 1 over c sub 2. All right, let's bring everything together with our key takeaways. Now, before we wrap up, I want to point out a few common pitfalls where students often lose marks, so please pay close attention to the next slide. Common mistakes to avoid. First, be very careful not to confuse no solution with infinitely many solutions. This is a crucial distinction. Remember, if you are performing the substitution method and the variables completely disappear, you must look closely at what remains. If you are left with a true statement, such as 0 equals 0, then you don't have an inconsistent system. Instead, you have infinitely many solutions, meaning the two lines are actually the exact same line or coincident. However, as we discussed in our taxi fare example, if the variables cancel and you are left with a false statement, such as 0 equals 5, then you are looking at an inconsistent system with no solution, where the lines are parallel. Second, please avoid the temptation to assume you've made a calculation error. It is very common for students to see the variables vanish and immediately think, wait, I must have done something wrong. If you have double-checked your arithmetic, re-verified your substitution, and the variables still cancel out to produce a false statement, do not panic. Trust the process. That mathematical contradiction is actually the definitive signal that the system is inconsistent. Finally, pay close attention to how you write your final answer. A common mistake is to write the answer is 0. Remember, 0 is a specific numerical value for a variable, but it is not the solution to the system itself. In this context, there is no value for x or y instead. You should clearly and formally state that the system is inconsistent or that it has no solution. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. As we've seen throughout this tutorial, identifying these systems can be tricky, and there are a few mistakes that even experienced students make. With that, we have covered everything regarding identifying inconsistent systems. Great job today.